Hello, class. Okay, this is a simple lesson in how to correctly draw the total product, average product, and marginal product functions. So first, think about what's on your axes. This is units of labor down here. In your book, sometimes it calls it the variable input, but I think intuitively it's easier to think about it as units of labor. And on this axis over here, this is physical units of the output. So this is not dollars like in supply and demand. This is physical units of the output. I hope you can see that if you had no labor whatsoever, even if you had a factory full of machines all hooked up and ready to go, if there was no labor, there would be no output. So this is the first point on the total product function. And then as we increase labor, output would increase. But what you have to remember is that there are certain restrictions. The assumptions are that we have fixed capital equipment, fixed technology, and all the workers are the same, which we say homogeneous labor. So under those assumptions, or to put them into layman's terms, you have some factory, there's machinery in there, it's all hooked up and ready to go, but there's a fixed amount, and there's no labor. So when you add labor, at first, output goes up just a tiny little bit because those one or two workers are running all over the place trying to get everything done. But as you hire more and more workers, output increases at an increasing rate, and finally it begins to level off. We say output's increasing at a decreasing rate. It finally maxes out someplace, and after that, if you hired more and more workers, output would actually fall because they would be crowding each other. So that thing is called a total product function, and it has 2 points that are kind of important. One is up here at the top, and let's bring that dotted line down. So that's the number of workers that generates the maximum output. And the other place that's kind of important is where this function is the steepest. It's called the inflection point. It's kind of hard to see, but where I'm sitting, it looks like it's about there. And that's the place where when you hire that worker, output increases at the fastest rate. Now remember that we've made an assumption that there's homogeneous labor. So you might ask the question, well, how is it possible that each time we hire a worker, output increases at an increasing rate, and then later increases at a decreasing rate, and finally actually decreases by itself? The reason is because at first when you hire workers, each worker can specialize when another is hired. So rather than have one or two workers running all over the plant trying to do every job, workers can specialize and do one or two jobs and leave the other jobs for someone else. And in that specialization, there are gains. So this zone right here, from 0 to that first dotted line, is called the zone of specialization. But eventually, all those gains from specialization begin to play out. And when you hire more workers, that would be in this zone right here. As you hire more workers, output continues to go up, but it goes up at an ever smaller and smaller amount. So that's called the zone of diminishing returns. Diminishing returns. And then it sounds a little bit weird, but you could continue to hire workers beyond the capacity of the plant to produce anything, and output would actually fall. And that doesn't have a fancy name, it's just called zone 3. Zone 3. Now the next thing you want to think about is, well, what is the relationship of marginal product or marginal output? Well, remember, marginal means extra, so marginal output or marginal product is the extra output that you get each time you hire another worker. So as you go along here, rather than keep track of the total output, we want to keep track of what's happening to each worker as we go along. I hope you can see that it would be 0 in the beginning. That one's easy. And also it would be 0 way out here. This worker right here, when you hired that worker, contributed no output. Can you see? Because we're up here on this flat part. So when we went from this worker to that worker over there, output didn't really move at all, or maybe it moved just a terribly small amount. So that worker's contribution is 0. And beyond that, these workers over here, their output or their contribution would actually be negative. So what happens is that as you hire these workers, the first one, the second one, the third one, when you're in the zone of specialization, output per worker is going up for each one. Finally, it maxes out here at the end of the zone of specialization. Now it begins to fall. It falls when finally you get over here to this place, this peak spot. Output per worker is back to 0, and beyond that, I'm off the page now, but beyond that, it would be negative. So that's marginal product. The only point that's really hard to see is average product. And the reason it's hard is because there's a condition of scale, like the scale that we've defined by this marginal product curve must be consistent with the scale for the average product curve. And here's how we see that. When output is going up and up and up, average product, that is the output per worker on average, would also be rising, but at a slower rate. You can see it if you think about, imagine you had a class and you took a test every day, and you made like 50 on the first test, 60 on the second test, 70 on the third, then 80, then 90. I hope you can see that your average would go up every time, but it would be going up at a slower rate. So average output's rising, right? Now, when you get here, average output per unit would still be rising even though the output per worker is now falling. So that would be like in that test example, if you made a 50, then 60, then 70, then 80, then 90, and then maybe you made an 85, your average would still go up as long as your average was less than that particular grade. When you make a new grade, whether it's higher or lower than the one you made before, as long as your average was less than that, it would pull your average up. And that's the same thing that's going on with this average product curve. So it will continue to rise until it hits the marginal product curve, and when it hits, it will stop rising and begin to fall. It will look like that. There is a little construction about that. It's not given in the book, but this point right here, if this were a face-to-face class, I would spend a lot of time talking about this. But this point right here, where the average product and the marginal product curve meet, is exactly the same as if you took a ruler and you drew a line from here to that production function, where that line is tangent, would also be the same as this intersection down here. It's really hard for most students to see why that's so, but if you think about the formulas of these two functions down there, it's a little easier to see. Average product, its formula is total product divided by labor. And if you can remember your old algebra days, you can see that the slope of this line right here is exactly total product divided by labor. Any line you draw from the origin over here to the total product curve, no matter what, any line, its slope would be total product divided by labor wherever it hits. And marginal product, for those of you who've ever had calculus, is just a derivative of this function. It's the slope of this function as you move along. And at this point right here, those two things are the same. The slope of that ray from the origin, the blue line, and the slope of the original function are exactly the same at that tangent point. It's not so important that you remember that, but and it's not in the book, but that's how you draw the total product function and marginal and average product. Okay, hope you found that helpful.